This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
At the same time. Okay, so you can pass that around. This one here is got a different material, and this one here is designed to show that this is the mass flow. It will actually handle pretty horrible... Oh, actually this one here won't work for a while. It actually shouldn't have blocked up. But here, what will happen here is that you'll actually get what we call a rat hole. And see, this one here, there's a hole right down through the middle, and that's very dangerous because if you get a rat hole, and that happens with grain silos and things like that, people actually sometimes get put in down a rope in here to try and clean out rat holes, but they end up getting smothered in the grain when all of a sudden it gets released, and people have died in Australia with rat holes and things like that. So this one is to show that this one flows not too bad. This one here, you'll actually get a rat hole. And so that's going to be very, very difficult to solve. These two here, I think they're pretty much the same as the first one, but you can, if you want to, somebody, get bored, you can actually time it, and you find out that the funnel flow actually empties faster. The funnel flow is good because it doesn't have material sliding down the outside. This one here, the mass flow, it does actually, the material does actually scrape and scour, but there's some reasons why one might be chosen above the other, okay? Now, because we're really getting into the area now where we're going to start looking at conveyors and looking at some of the friction and powers. Now, actually, I've got some rice here. Now, when I go like that, why does the rice actually go on an angle? Why is the rice on an angle? I'm scaring you, aren't I? Because I ask these hairy questions and not quite sure what to say. It's because of friction, okay? Now, if this rice was water, or what I could do is I could get a big pile of sand, and I'd have a big cone of sand like that. It stays up like that with the angle of repose. But see, if it was water, where you've got no internal friction, you'd be a puddle. And so the thing is that solid materials, it's because there's a lot of internal friction and things like that. And I want to demonstrate. Are you able to come and give me a hand? Okay. Now, can you just hold that up there? And what I'm going to try and do is see if we can actually, without spilling it all over the place, I'm going to put some... Oh, okay, just show everybody that that goes up and down. Okay, pretty easy, eh? Okay, right. Okay, now just move it up and down. Oh, so I probably put a little bit too much in already. Okay, but you can pull it up and down, can't you? Yeah. But, okay, now look, we don't need to put, we'll just hold it up to there and pull it, push it over to the side so I can put it just a little bit more in. Okay, try that. So it really gets locked in. Okay, so that is the kind of friction forces. So that, when I first saw that, I thought that was an incredible thing. I just was just so astounded me that that's why I decided to make it up so that I could come to Melbourne University and show the students. But no, so see, it drops all right, but then you might want to try it afterwards, but look, it's plastic.
I'm sure everyone would like to have a turn if that's okay, right? I'm sure everyone would like to have a turn.
Yeah, we'll just pass it around. Okay, now, so we're up to there and we've got the PowerPoint, the handout. Right. So we just go back and we just do a little bit of revision on. So can we get it up on this one?
Now, both screens have got your
Okay.
tutorial problem, but I can easily put one of the screens. Which one would you like? That, as soon as it comes up, that one is, or vice versa. Which would you like, Brian? Flip it.
Keep the computer with that one up there.
Okay, sure, I can do that.
No, I won't get messed around. Okay. Now we're just going to do a quick problem just with the sheet. So you've all got the sheet? Right. Okay. Now, I'm dreaming up a problem where we're going to actually use some coke, and the coke is 0.8 bulk density. Okay? So we're coming in here, 0.8, because remember the arrows, the red ones are where we're coming in. And we've decided that the coke's got to be instantaneously, now it's not, we're going to use, we want to come up with a conveyor that will convey two different materials at two different times. We're not mixing it on the belt, so instantaneously we want 400 tonne an hour of coke. So we come in here at 400, right? And so we've got, this is coming down here like this. Now we come across here, and remember we come down here, and we come across in that line there. Okay, everybody with me so far? If anybody wants to say stop, but I'm going to carry on. Okay, the next piece is we want to put in an ore. And so the ore, because if you're going to do some smelting or something like that, if it's a sulfate ore, you want to actually have the carbon to be able to take out the oxygen and the sulfur and that kind of thing. So, okay, here we go. So we're going to have 800 tonne an hour blocking up. Need highlighters. But okay, but we'll say that the bulk density of the ore is the 2.5. So we're coming down here. Coming across here, this is the ore. We're coming down. Oh. 400. Yeah, okay. So we're coming across here like this, down here like this, and we're coming across here on that line to there, right? Okay, everybody sweet so far? Right, now, we've got some restrictions. Because the ore is very abrasive, we don't want it to actually come at a higher velocity and take out all our chutes and abrade the chute. So the lining on the chutes are going to limit us to about 1.1 metres per second, okay, in speed. And then because of the coke, because of its dustiness, we don't want it to go faster than 1.1 either, okay? Now, so when you have a look at it now, and we'll assume that we've got 30 degrees and we've got the 20 degrees surcharge on it, so that complies with this information up here, 30 degree trough, 20 degree surcharge. Okay, which is the best belt that's going to do it for both materials? Who's going to be first? What belt width do we need? Remember, we're limited to 1.1 metres a second. We're playing with toys. Okay, look what we'll do. Here is 1.
Right, so, just because that writing more, why don't you use my pen just so it's a little bit less intense?
So here is 1 metre per second. We said 1.1. But we come up here, and so the belt width here then is saying we need 900. This one here along here, here's 0.9 and 0.12, so we'd have to go for the 0.9 at the moment, and so we'd come up here, and it's saying we need a belt width of 1200. So if we're going to have two materials being able to go on the belt, how wide's the belt going to have to be? 1200? Everybody agree? Okay, but now I said we're limited to 1.1. So that actually here pushes us pretty close to the 1.2. So we might, and if we can come down to this 1.2, we might be able to come up with 1,050 wide belt. That would be a bit cheaper. The idlers and all that kind of stuff would be a bit cheaper. What could I do that I could investigate to actually get us to go across here just a little bit and come to a smaller belt? Remember, have a look at what's set up here and have a look at that arrow there. What can I do? Can you understand? How do I get extra capacity on my belt?
By having a bigger tire.
Right. So if we come from 30 up to 40, what does the table tell us? How much extra capacity do I get? Here I go from, here's 30, I've got 1. Here's, well, if I go up to 45, I go up to 1.15. So I've gone up by 15% in capacity. And see, 15% in capacity will give me that from 1.1 to the 1.2. And so that's only 10% increase in capacity approximately. And so then I will be able to get away with it. So if I wanted to use the 10,050 wide belt, because I've got a whole heap of spare, all the other conveyors all around side, a 10,050, I don't need to go and buy a special belt. All I'm going to have to do on this one is just make it, instead of 30, I just need to make it 45. And I can get the extra capacity out of it. Okay, so you can see, you can do an awful lot of stuff here, that if you had to actually do that by a string of calculations, you know, you'd have a few pages, but you can actually do it here very quickly with a bit of sensitivity analysis. Okay, we're all right there? Okay, now what I want to do is talk to you, because I think it's coming.
This is really important. Everything's examinable. Any questions?
Oh, that might be a hint.
Ask Brian to do this. It's not going to be hard, just for turning up and you get your idea what he's doing. It's like a paper-based calculator. Everyone good? Fantastic.
Okay, now we're talking about the resistance. So you can see the resistance. That is pretty phenomenal, isn't it? That just a bit of rice actually can block that up. But that's the principle of rock bolts. You know, when they actually put building sites and things like that, they drill in and try and pin it in on the ground and all that. It works pretty much the same kind of thing like that. Okay, now, what we're going to do is we're going to talk about resistances and belts, and that gets us onto that second handout that I gave you. But so, look, when the belt's going along, we talked a bit about sag. In our example, it was pretty tight, so there wasn't much sag. But when it's going along, normally the belt will actually go up and down like that when it comes along the idlers. All right? Okay. Now, when the belt's like that, see, it's pushing the material in, and that's difficult for it to do. When it actually goes over an idler, the material actually opens out. So the material's sort of opening out and then getting squashed and then opening out and squashed. So there's an awful lot of movement. But then that's just in that way. But when the belt's actually going along too, it actually flattens out just a little bit, but then gets squashed. Flattens out, gets squashed. Flattens out. So there's a lot of movement, lots of resistance. And I don't think we're going to have time to get to pipe conveyors or tube conveyors. But people actually make conveyors like that. And they have to have, instead of 3 idler rollers, they have to have 6. And so what happens with that, you're tightening up the tube's lifting off, tightening up, and the power on a tube conveyor is twice the power on a conveyor like that. Okay? And so that can be quite interesting. So let's have a look. Get this. So we've actually got here up the top, yeah, I can do it here. Okay, so we've got belt and material lift. So, okay, if we're actually going to hike it up in the air, that's the row GH kind of thing. so that'll come out when we get onto the piece of paper. Material trampling, that's what I've just sort of said, the movement and trampling the material, so the material's moving all the time. We've got idler alignment, that's really important. Rubber indentation, so when the rubber's actually going over the rollers, the rubber's actually moving in and out, so that takes energy and all that. Now, if you tried to do that from first principles, that would be a heck of a job. So what we do is we learn from other people. Okay, now, the thing, I'm not going to go too much into this. This starts to get a little complicated, but if you look in the Dunlop manual that you've got access to, it'll explain it. But some of the engineers that I talk to in industry, they get a bit confused. Well, first off, TE is in your handout is labelled FU. It's a bit like, you know, F equals ma. We all know that the A is acceleration. But when we do, you know, vehicles going down roads, we use S equals U plus FT, and F is the acceleration, whereas in the F equals ma, A is the acceleration. So here, in bulk materials handling, stuff is a bit interchangeable. But here, the effective tension, you can change T1 and you can change... let's say you've got a bicycle chain, right? Now, the effective stuff, the torque, it doesn't. That's not going to change if the chain is slack or tight, and I can actually over tighten the chain, and it's not going to be too good for the bearings. But on a belt conveyor, you can actually over tighten because you want to not have too much of the movement over the belt. You want the belt to be nice and tight, particularly for edge spillage and stuff like that. So, but anyway, I think I've said enough on that. So this is mainly for other guys. So this is about the trampling. And one of the things is here, just down here, if you go too fast, coming over, everybody see where I'm pointing? Yeah. Okay. When it's coming over here, if you're going too fast, the material can take off. And you don't really want to have materials starting to bounce around and all that kind of thing.
The material's going left to right on the screen, correct?
Going that away. So there's seats where it's lifting up. So the belt's going that away. So it's just coming along, and see, it's just come up and over, and it's taking a little while before it actually comes back onto the belt. Okay. Now, so what we have to do is, fortunately, it's all been worked out for us, but we're going to end up now having another look. We've looked at the, sorted out previously, the speed and the belt width. We're happy with that. Now we've got to make sure that we keep in mind 1725 tonne an hour, and then we've got about 18 metres lift and about 80 metres horizontal. So that gets us to this next sheet. So you need to be aware of this sheet here. Have you got that sheet? Now, in the Dunlop manual, you'll find, and look, and even the standards and that kind of stuff, there's three main equations. The equations have got lots of factors in them, but there's three main equations. What you do is you have a look at the unloaded conveyor. And so you're just looking at all of the idlers turning around and the head pulleys and all this kind, and the belt bending over. So it's got nothing to do with the load, right? And then the next one is, and so that's all summarised in that chart there for you. And look, usually this chart is a sort of a first guess, but quite often it helps to clear your thoughts and you know where you're heading. This one here is when you're actually moving the material horizontally. This one here is when you actually raise the material. Okay, and this is just virtually MGH. So now we come in here, so we know that our belt width here is 1050, so we're coming in here. We know that the conveyor length, the horizontal length is 80, so we come down here and we pick up this number here, which is 2.4, but we've got to remember that this is here for each 1 metre per second. But how fast was the belt going? It was going at 3.1 metres per second. So we've got 2.4 times 3.1. So we end up with 7.4 kilowatts. Okay? So that was a pretty quick way of doing power. So what we're really doing is we're just checking. Remember, we're doing a forensic investigation of that conveyor that's at Whyalla. Okay? Now, the next bit. So see here, they weren't talking, because it's empty, they weren't talking about tonnages or anything. So we've got 7.4 when we're actually running it empty. Okay, now here we're going to convey the material horizontally, so we're actually putting burden on, and it's doing, you know, all that frictions, tramping. So we're coming in here, and so look, it's somewhere between 60. So we said about 1800. So we're coming in between 16 and 20. 2000 there. So we're coming along and we're picking a value here, and then here this is the length. So if we do a quick rough interpolation, we get 16. Okay, so 16 kilowatt. Happy with that? So see, pretty easy, because if you have a look at the equations, which you should do it in the Dunlop book, you'll find that they're pretty horrible things. But it includes all the friction and bearings and all sorts of things. And sometimes it's actually quite good look up when you're actually designing a machine or something like that, and you want the friction of a bearing, because sometimes it's pretty hard to get. But if you jump into conveyor books, you pick it up a lot easier. Okay, now it's a bit like when you're walking along the road. You feel pretty easy until you come to a bit of a hill. And this is what happens. And so what we were doing here was we were going up, how many metres did we say we were going up? On the previous slide, it said that we were going up 18 metres. Oh, okay, sorry, this one here, that was tonnes per hour. Yeah, tonnes per hour was 1725, so that's why we came in 1725, we came in there. Yep, so about 18. And then we're going up 18 metres, so 16 to 20, so we're coming down the middle there. So we actually, here, we're coming in and we're interpolating around here, and so 90, you've got the four figures, so the middle one is about 90, okay? Now what you do is you add that up, 7.4, 16, 90, and you get up about 115. And when we have a look at
You up, Ron? Do you want me to put that one back up?
yeah, please.
Yeah, sure.
Question. Where did the 3.1 come from again?
Oh, we're just getting it up.
Ah,
Right, okay. The 3.1 came, because it was here a couple of days ago, we looked at it. The 3.1 was their selected belt speed. Now, we realised that it seemed to be a bit faster than what we needed, but remember we were a bit confused because the burden isn't exactly the way it's on our chart, because we didn't have the surcharge. You know, on the photograph that I took, it was fairly flat. Okay? So that's where we got the 3.1. Know where everything else came? Okay? And so what we found here is that we calculated 115 in their drawing. They said that there was 125 kilowatt. They installed a 132 kilowatt motor. Do you know why they didn't install a 125 kilowatt motor? Because mechanical guys aren't electrical engineers, and electrical engineers don't make 125 kilowatt motors. And it's funny because the next one up is 132. And you kind of think, oh, 125 seems a better number to go for, but they decided that the number will be 132. And in the Dunlop book, it's really good because they list, well, here on this table across here, it's really good because they actually list the belt sizes. I've had managers come to me and say, oh, just change the belt width by, 50 millimetres. Well, you don't do that. You have to buy them off the shelf. Well, you can get it, but what they do is they end up having to put it through a machine and they'll actually cut the edges off. they'll sell you a big one, a wider one, and then they'll charge you more to actually cut it if you want a particular one. But then you'll have to buy your own particular rollers and all that kind of stuff, and that would be daft. So here, these are all the standards, and then if you look in the Dunlop manual, you'll find all the standard electric motor sizes. Okay? Because sometimes all of a sudden, if I haven't got that close to me, or the Dunlop book, you kind of think, oh, for crying out loud, what's the next size electric motor up? So if you're doing a job somewhere and you need to know all the different sizes of electric motors, that Dunlop book is pretty good.
Can I ask a question? I get when an electric motor has to lift the burden, but isn't gravity going to help us lower the burden? Because the power to raise or lower the burden.
Yeah. No, okay. Remember, if we go back and can I just click? Oh yeah, okay, I can go back. Look, remember that the conveyor that we're looking at is this one. Okay, so we're actually lifting. Now, if we're actually going down, we could actually generate some electricity, or we'd probably have to put in brakes and all this kind of stuff. And so, particularly belts that actually go up and down like this. Over some distance, they can be, you have to look at each bit because some you'll actually be putting power in, some you'll actually be getting power out. And so, and look, some of those ones, they end up having to put brakes, and you've got to try and discharge heaps of power pretty quickly through brakes. And, it's a bit like landing an aircraft. When you're trying to stop an aircraft, those brakes can get red hot. Okay, so we'll just go past here, get back to where we were, and right, so now what we've done, so see the actual there was 125, and we're sort of saying, we're not quite sure about that 125. So now when we actually look at this, okay, I'm just saying if you want to do, for bucket elevators, a quick check, just chuck that in, but allow probably about an extra 5 metres lift or something like that for dredging down the bottom, and you'll be right. So quite often if somebody says, hey, what's the power of a bucket elevator? I just jump straight in onto that table and add an extra 5 metres for some extra friction, and that's going to be pretty close. Okay, now what we're going to do here is quickly have a look at the tensions. Now, so that's this is the way the tensions actually arise now. The tension, we use the belt and we come... Oh,
sorry. No, keep talking your phone. I'm just going to put both up.
So now what we're going to do is we're going to have a look at the belt tensions. Don't think... Oh, that actually got the... okay, now the tensions are here. So what we might have to do is we just might have to go backwards and forwards a little bit between these slides. So there's the take-up, remember? And so we'll have a weight under here. So essentially what happens though, if you start off here with T2, so that's the minimum tension, but the T2 comes from here. See, so here's 25 kilonewtons, and then around here, and see, essentially it's still about 25, okay? Now, the difference here between is the when in brackets is when it's starting, so we don't really worry about that because it's very transient. So 25 plus 25, and so you end up with 50, which means that you've got a 5-ton counterweight here. Okay? And so now, and even here, see, that gives 25. So we've got 25 all the way. So this offset from the belt is all 25. Around here, 25, 25. But here, then all of a sudden, the offset gets greater and greater and greater until you get to the top here. And they actually are saying that they've actually got about 62. When they start up, it's about 84. And then as you come around here, you've got your slip and all that. So that's your E to the mu theta thing. Okay, now if you turn to the back of that sheet, you'll end up seeing where we've actually got the T1 and the...
I can just drive. I can just make use of the document camera and I'll do things here for you. There you go.
Right. Okay, so what we've done here is I've summarised what happens, and so the F1 here is your T1, this is your T2, and now this was the TE, quite often they talk about the equivalent tension to actually get it to drive, but they actually call it FU here. So FU, so we've already worked out, oh, no, we haven't yet, have we? Because here we go now, we've actually got TE, or, sorry, that should have changed that to FU, but it's 115, because remember, that was 115 kilowatts, so we ended up getting off the other side. We added it up, we got 115, and then we had 3.1, and see, I get lazy because I can't do that in my head, but anyway, we get 38 there, 38 kilonewtons. So that's the maximum tension, the equivalent tension to get it to drive. Now, T1, so that's the change in tension around here. T1 is equal to 1.5. Now, this is the e to the mu theta thing, and times the 38. So it's the TE. So it's a bit funny that you don't actually calculate T1 and T2 first. I actually asked a young guy, I said, you know, I want you to do some calculations for me for a conveyor. And, oh, no, sorry, I'm going to run out of time. So anyway, okay, so what you do is you take the 1.5. The 1.5 is listed here. Get my finger around the right way. It's listed here. So that actually takes into account that you've actually got a wet rubber head pulley, and you've got 180 degrees wrap. So this is the wrap here. This is just a little bit more than 180. But if you take 1.5, that's what you'll generally find in industry, okay? If you decide to snub this and bring it around here much tighter, well, then you can actually reduce your friction. If you actually put ceramic on here, you can reduce the maximum tension and that kind of thing. But okay, they hadn't done it on the site, so we're just going to check. So we've got here, we're bringing that 38 down there, we're multiplying it by 1.5, and then so that gives us T1. Now, we've got 57. They ended up here having 62. Okay, now T2 is T1 minus TE, and so we've got 57 minus 38 in 19. And so they actually here have 25. So there's the 25 here, right? So now, we've got 25 there, but we in our calculation, we've got 19. So we sort of say, hey, what's going on here? But if we have a look at this, what's happening is that they actually, we're 6 out here, and we're also 6 out there. And so because we're 6 out, you kind of think, hey, what they've done is they've increased the tension of the belt to stop it from sagging. And if we went right back in the slides, you'd see that that belt had absolutely no sag in it at all. It was dead straight. And normally on a conveyor, you limit the sag to about 2% or something like that, so there'll be a little bit. But in this instance, they're actually putting the bearings under a little bit more load, so they've put an extra 6 on. And so that's how our calculation then is pretty right. All they've done is they've put a little bit more in the counterweight. So the counterweight here, we've come up now to 25. So they put down here, they put a little bit more mass in here, which is unnecessary. So if they wanted to, if they were having trouble with lots of belt splice failures or something, they could take a little bit of mass out. But so there was no problem with that. Okay, but now the sag, they could have reduced the sag if they wanted to by putting the rollers closer together. So instead of having the idlers are normally about 1.2 metres apart, they could actually put them in, but then you're doubling your cost. Okay, so it's probably easier to keep up the tension. Right, okay, now for overland conveyors, the rolling indentation is here, one of the greatest resistances. And they're doing a lot with these big distance conveyors here, here to try and actually overcome this. See here, when you look along, you can see the indentation. So that's empty, see, all the way through. So you're getting indentation. So what they're doing is they're coming up with stronger rubbers and that kind of stuff. And look, a lot of it is in-house. You can't get the information. So you've actually got to buy it from other people. And so normally it's easy to do stuff in industry, small short belts and that kind of thing. If you're going to do an overland conveyor, get somebody else to help you. I don't think we need to talk about that. This is about the belts. Here's an overland one. We'll just quickly go through this. I say leave it to the experts. Now this one here is pretty tight. You can see that there's not too much sag there, but mind you, at the moment it hasn't got any material on, so we don't know. That thing there is to keep the belt on when there's strong winds. And, you know, the belt might actually go off to the side, but you don't really want it to go on the ground. But coming down here and starting to go around corners, it starts to get interesting and it gets a bit counterintuitive. Because here is a conveyor going around a corner, but see the belt wants to come inside, but where's the materials going along, it wants to get flung out on the outside. So this is one of the reasons why here you end up having to have this, and you kind of think, hey, this is a little bit... it's not like driving around the camber on a road. You know, the camber on a road is trying to help the car from sliding off. Here, you've actually got to camber it this way to stop the belt coming off this way, but material makes it a bit easier to shoot through. So there are complications. But anyway, what we want to do is, and look, there's different kinds of belt and that kind of stuff.
Can we jump to the motor issue?
Yeah, that's what I'm going to do.
Just jump straight forward.
Yeah. Okay. So when you see something like that, is that pretty normal wear to you? Indicate what forensically when you see that? What does it indicate? Misalignment, bad misalignment. But for it to go for that long and to get that bad, people don't look at these things sometimes. Look at this belt here. This is a take-up. There's a whole lot of material dropped inside of the belt, and so material here is just going round and round. There's lumps. They're just about ready to pop through the belt. So what you should really do is you have these here as self-cleaning drums. So that any material gets in there, it hopefully will actually get out to the edge here. There's a sort of a spiral inside there. This one here, try and get it. Okay, design consideration. Quickly, if you have it, like sometimes they get a bit worried about the belt getting jammed up there, so they do this. But then this means that it's unidirectional. If you go this way, you'll be right. If you come this way, you'll steer the belt off and you'll have it on the ground. So there's problems there. That's in a mine. They actually suspend all their frames and idlers and stuff from the roof. Here's a motor. Now we're starting to, this is not a typical one, but what happens with this, where you actually, with the motor and the gearbox all inside the head pulley, people are actually using these on mine sites and things like that too now. But these are probably more the type that you use in supermarkets on the checkout thing. But one of the big problems is when you get high kilowatts, you're having trouble getting rid of the heat. Because, see, this would normally have a rubber lagging on it, and so you can only get heat out here. And so what they do is they fill the whole thing up with oil, and the electric motor works and runs in oil and everything else, trying to just get the heat out the ends. And so that's the biggest problem with these. Okay, here's some motors. I put this in because I like the self-aligning motors. You don't have to worry about couplings and all this kind of stuff. They're shaft mounted. You've got tight connection between the motor and the gearbox to keep the dust out. And I like the motors mounted vertical because then when you've got the fan blowing the air and it brings in dust, it helps to keep the cooling fins on the motor clean, whereas a lot of people put the motors horizontally and they just fill up with muck. And fluid couplings, look, they went out with the ARC. People still use fluid couplings a bit, but we've got triple VF now, so that's a variable frequency drives, so that's what you do. Okay, this is a problem, and this is one of the reasons why. So we've still got about 10 minutes?
Yep, so you can really slow down and just relax, because this is
okay.
Also examinable.
Right, because this is very interesting, because I do an awful lot of checking of calculations from other people, and people have come a gutser with this. What happened here is I ended up getting called into a place, and this one here was a 10-inch, 250mm shaft, about this big, and it had actually broken. And I said, Brian, what's gone on here? Well, forensically, what did we learn about the chalk when we did the chalk test the other day? If it's bending, it breaks flat. If it fails in torsion, it breaks 45 degrees. So fortunately, I could remember busting a bit of chalk, 30 odd years ago. And so I saw this shaft and I thought, hey, there's no 45 degree bits on it. It's all flat. And so I thought, hey, this looks as though it's failed on bending. But how come, it hasn't sort of got... But anyway, then I thought, hey, fatigue. And fatigue, when you get cracks, you get the crack propagation, and it doesn't happen straight away. It takes time. So I said, what did you guys do to this about 6 months ago? What did you do to the mount? And this is what it was. Okay? You kind of think, well, that's not too bad. So anyway, we started to have a look at some of the forces. Now, so if you've actually got a torque coming that way, that's actually then going to end up putting tension or compression in that bit there. So there, we've got it. Okay, is that all the forces that I need to put in? Think about doing free body diagrams. Is there a force missing?
Yes.
Remember, okay, if I've got a torque, but I actually do it with putting in with two forces, I've got one force up and I've got one force down. Okay, if I've got a real wheel brace on the car and I'm trying to actually get this blooming nut off, and I jump on the wheel brace to try and get that nut starting to undo, if I jump on here, the wheel brace wants to go down here, but it also is putting a force here on the nut, and it has to be reacted, right? Okay, we happy with that? So there is another force that needs to be applied there. If you forget that force, and that's what happens when I check people's calculations, they keep on forgetting that force. And in one instance, it was a 50-ton force. That's a big force to forget. And you can put it into your blooming computers and all that kind of stuff. You can get an answer, but if you don't put in all the forces, you don't get the right answer. Okay? So what did they do? What had they done wrong? So there was nothing wrong up till this point. Okay, so this had gone for years. But then they decided that this was attached to a walkway piece, so they wanted to actually change that, and they decided that they would actually put in like that. We changed it all that much. Just stop and think about it, because it is a disastrous change. Because what's happened here is that the torsion, the force, there's going to be a force here, but we've actually virtually now got a linkage between here and here with a force there. Now, if you are out in the bush somewhere and you get bogged down in sand or something like that, if you've got a, is this a whiteboard one? I don't want to go on permanent marker, whiteboard marker. Okay, if I've actually got a tree here, my car's bogged down here. Now, if I put a rope between here and there, what do? Do I try and help pull that way, or do I try and pull it back this way? I try and get that as tight as I can, because if I then pull this sideways like that, I end up with a force triangle like that, and a little force here is going to give me a big pull. So what's happening here is that there's a bit of a force here, and it wasn't too small, but it meant that I had a ginormous force through here. So, and I didn't have that before. Okay, remember before when it was out here, there's no force between there and there because we've got a bend here, and it can move. Here, as soon as that tries to move, we get a force coming through there, pulling it together. So what do you reckon they should have done? I hope you're thinking and not going to sleep. But anyway, okay, it'd be a disaster, I already told you that. Okay, That would have been a better solution. So can you, am I describing it? Do you understand what's happening there?
Describe it, right.
You're reacting the force of that coming around there, but here you can't pull those together. There's no force bringing it together. And that's why I've just decided to put it in this lecture and talk to people about it, because I've seen it happen, just myself, in about 3 different instances. And so I would rather you guys learn from other people's mistakes, because I tell you what, when you bust a 250mm shaft on a piece of equipment, it doesn't just get fixed overnight. You could have that piece of equipment down for 3 months.
Just so everyone in the room gets it, Brian, do you mind if I'll have a try to see if I can do a 3-body diagram for what you've got up there. Big torque being applied. You've got a prismatic joint down here. The resistance, if this block wasn't there, the resistance would be, block wasn't there, it's going to stop everything. So we'd have a resisting force there, back up to the shaft, bending.
Yeah, because the motor and gearbox is all supported off the shaft. Okay, so if we go back to where we had it, down here, this bit here is really not taking all that much weight. A lot of the weight here is actually taken on that. This will balance a bit. Look, there'll be a little bit of weight there. It's certainly not 50 tonne. That doesn't weigh 50 tonne. But by having the torque here and a very slow gearbox and everything else, so the torque was way up. So you could actually get into that disastrous situation. So that's one of the reasons why we broke that bit of chalk yesterday. This is.
Is everyone with you? Everyone with my eye on that particular problem? If not, that's fine. Yep. Fantastic.
Okay.
Brian, you've got 3 minutes to go.
Yeah. Okay, look, this is a way, if you've got a really long belt, you kind of think, how on earth can I actually get some more power into it? Because it's one of those kind of things you don't want to keep on bringing up T1, if you can actually put some power in halfway along. So here, this is a good way of actually getting the material coming over, so you just bring it up and back. But see what's happening though, this pulley here is working on a dirty belt, and so that's when you need a slatted one probably. And then there's a bit of fall here. This is an interesting way of doing it without having the material fall, is that you actually sit the blue conveyor onto the red conveyor and let the friction between the blue belt and the red belt end up giving it a bit of a tug along. And so that's not too bad. Okay, trajectory. Yeah, this is good for you to see, because most people do not understand what happens in a bucket elevator. So this is a trajectory. Look, there's about discrete element analysis and all this kind of stuff here. They come up, look, they're not even getting really very close. They like to think they are, but what they do is they eliminate all the particles that are below 20 millimetres in size, because the computers just can't keep up with all the stuff. But it's your fines, I've told you, with some of the stuff there, it's the fines that cause you the problem. But the trajectory, there's about 6 different ways you can calculate it, and they're all different. But sometimes when you're looking at your linings and things on chutes, you need to look at it. But bucket elevators, most people do not realise that that's the way centrifugal bucket elevators, they think that the material comes out of this bucket, falls on this one and slowly, just discharged later. Yet, because, see, with you guys being mechanical engineers, as soon as you come up here, and then as soon as you get into that curve, that's immediately there, you're starting to get the acceleration of V squared over R. And so that's why here at 9 o'clock coming up, that's when the material starts moving in the bucket, and probably at about 10 o'clock is when stuff is actually starting to come out. And a lot of engineers have got absolutely no idea that that's what's going on. So this is a good picture, and I surprised a lot of people with that. But I think that's maybe where we should stop. But if you can get that buried into your head, and a few of those other things, and look, some of those frictions and things like that, you know, you wouldn't be able to work some of those frictions out by first principles. You know, that thing with the plunger, you know, it's amazing when you actually only got about 2 cups of rice that you can have that kind of effect. And so really what I wanted to do is say, hey, be careful, don't think you know everything, try and learn from other people's mistakes, but there are a whole heap of counterintuitive things out there that are there to bite you. And so just be cautious. And anyway, hey, may I wish you all the best for your exams. Mechanical engineering for me has been exciting. It's taken me all around the world. It's taken me into a whole heap of different operations and that kind of stuff. And yeah, a good mechanical degree will get you into all different sorts of areas, and all the best for the future.
Thank you, Brian. Any questions for Brian just before we say goodbye?
Yeah, and I'd like all my toys back for next year, please.
If there's no questions, that's fine. I'll see you next time. If you want to just have a quiet chat to Brian, he'll be here for a couple of minutes while we back up. So thanks again.
Yeah, and I can, when we get out of the lecture theatre, I'm happy to talk outside. But you'll come across conveyors and bulk materials just about everywhere, you know. If you're working in a place where they bake bread,
Thanks very much.
I need to get that plunger back. Oh, so I've got to empty it.
Thank you for your time. That was very interesting.
Thank you. Yeah, I'll just put that there for you to look after.